The audio is on, right? Okay. All right. So, so yeah, I mean, I guess the vacation has been a little long, but I think the good thing is that we are kind of changing gears a little bit when we are starting with ADS-CFT. So hopefully, even if you have forgotten some of the things that we have talked about, today's lecture may not be inaccessible. But at the same time, unlike the previous lectures, what we will do today's is, obviously I cannot cover all of ADS-CFT. This was a full course that I gave at some point. So we'll have to kind of tell a story and, understanding the general picture from a general story is part of the skill set. So you should not underestimate that. You know what I'm saying? It's not like following everything step by step and deriving it is one way to do it, and it's necessary sometimes and it is important sometimes. But other times you have to kind of get the story from a minimal amount of information so that you can proceed as well. So this is also part of the skill set. So today I think we'll have to do the latter as far as ADS-CFT goes. And what I'll do is I'll spend maybe the first half an hour talking about sort of the string theoretic background of ADS-CFT, and that might contain a lot of words that you might not fully digest quickly. But the second half, or the parts that we'll really need for our course, should be, even that I will not do a complete job, but at least the story should be less mysterious. If you have not seen string theory at all, the first part will be a little bit, I'll try to make it familiar, and feel free to ask as many questions as you want. So today's lecture is kind of like an overview. So, I'll emphasize the parts that we will need for ADS-CFT in this lecture and the next one. But the first 30 minutes, or the sort of the introduction, or the Maldecena's original derivation, so to speak, of ADS-CFT is really stringy context. So you can't really, I think it's good to hear about it once at least. But even though it is not super important for the rest of this course. So that's where we'll start. So the stringy origins of holography or ADS-CFT. So note that string theory, people had talked about holography in the context of black holes, Toft and Susskind, but people had not really thought of string theory as a holographic theory until that point. And in fact, in Maldecena's original paper, there is no mention of holography, at least in the first version, I'm sure of it. So, but it was later that it was realized that this correspondence should really be understood as an explicit realization of holography. Okay, so and that's the attitude that we will take later on. So the duality between gravity or quantum gravity in asymptotically antide Sitter spaces and some certain superconformal or conformal field theories, that was the thing that came from string theory. And the realization that it is a holographic correspondence is what happened in a later paper by Witten and some other people, and that is the thing that sort of powered ADS-CFT in a certain sense, and that is what has given rise to, the sense in which it has kind of deflected the direction of research in the field itself. Okay, so because it's essentially what it gave us is a holographic definition of quantum gravity, and then you could use that as a tool to study things. So that happened in the second paper. So that's the approach that we will really focus on. So, but first I'll just tell you the original, so the culmination in Maldecena's observation of this duality. Okay, so duality does not necessarily mean holographic duality, that came later. So the duality is between certain gravity theories in asymptotically certain ADS 5 times spaces and some conformal field theories. Okay, so this was the proposed duality of Maldecena, and its origins were basically having to do with black holes and supersymmetric black holes and string theory going back probably like 10-15 years, so that's a long story. So in order to say a few things about it, I'll say a couple of things just to give you an overview. So the basic starting point is that string theory has two kinds of strings, or many kinds of strings, but at least two. Has closed strings and open strings. Closed strings and open strings. String theory is a theory in which you basically, instead of writing down a world line action, which you can write down for particles, you write down a world sheet action. So this is something that you may have seen, and it's not important if you haven't, but the key point is that there are two kinds of strings. at least two kinds of strings in string theory. One of them is closed strings and one of them is open. So of course you could have open with different boundary conditions. There's a variety of boundary conditions that you can apply to these open strings. So in some sense this is slightly too fast, but this is roughly the first observation. Okay, and the open strings, so the open strings can, in order to define open strings basically means that it has two boundaries. So the string has two boundaries, and one of the hyperplanes in space-time on which these open strings can end are basically what are called D-branes. Okay, so this is just a name for certain boundary conditions for open strings in string theory. Okay, so if you start with open strings, and then you quantize these strings with these boundary conditions, you will find the spectrum of the closed string, so spectrum of the open string, and so on. So you can do a quantization of this thing, and this is one of the things that you will do, for instance, in the first textbook on string theory. Okay, so this is one of the things that you'll do. So closed strings on the other hand they have a periodic boundary condition. So right now, so they will basically be this, and they will not involve any boundary conditions at the ends of strings. Okay, so the boundaries in space-time where open strings can end are what are called D-branes. Okay, so the point is that in string theory, if you have a D-brane like this, loop processes involving open strings. So this is a loop process, you can think of it as a open string stretched here, moving around in a loop. Okay, so loop processes in open strings also have an interpretation as an emission and an absorption as a closed string. Okay, this is completely trivial, visual fact is called, world sheet duality. World sheet duality, or sometimes open closed duality. Okay. Okay. So this basically means that whenever you have a D-brane or a boundary condition for an open string, so you have the freedom to reinterpret it either way you want. Okay. It's just from the mathematics of it, there is no real distinction. Okay. So the point is that, so if you think of D-branes as sources for closed strings, okay, so D-branes can be thought of as sources for closed strings. That means that the fields, so when you quantize a string, you will find various fields. That's the way in which string theory lands or connects with what we know about low energy effective field theory. Okay, so the way in which if you quantize strings, you will find, if you quantize a closed string, quantize a closed string, you will always get a metric. Okay, when you quantize a closed string, you basically find what is called a spectrum of the closed string. Okay, and similarly you can quantize an open string, and you will also find various things. I'll say what it is. So depending on various details, you will find a metric, what has an interpretation as a metric fluctuation, and then you will find what are basically called form fields of various kinds. Okay, so I'll just write down one example of this. So you should think of this as a generalization of F mu nu. It's a fully antisymmetric field. Okay, and depending on the string theory, so there are a few different choices that you can make in the definition of string theory, and eventually they turn out to all be dual to each other. So that's the sense in which people say that string theory is a unique theory. Okay, so but for a given string theory, there are, metric is always guaranteed to exist. Then there are a bunch of form fields that show up. Okay, so these are called form fields. Okay, so this is your the spectrum of this is the closed string spectrum. So depending on details of various things which we don't really care about, you can have, there will be different kinds of forms that you can show up, and the string theories in which they show up are sometimes called type 2a string theory, type 2b string theory, and so on. Doesn't really matter. So we will actually be caring specifically about a particular class of string theories which are dependent on some boundary condition choices and so on, which is called type 2b string theory. Okay. Okay, so but anyway, that's not the point here. The point here is that there exists closed string theory contains metrics and metric informed fields. There is also something called a dilaton, which is a scalar field, but let me not emphasize it. Okay, and a couple other things. So the form fields with pseudo form indices can sometimes can be thought of as dilatons and axions and various scalar fields. Okay, so in some sense this contains this. So let me erase it actually, even though this has a special status for some reasons. Okay, so anyway, so this is the spectrum of the closed string. And if you quantize an open string, on the other hand, you will always find a gauge field, okay, standard gauge field, okay? So, and some other stuff, doesn't matter to us, okay? So, the point is that if you have, the spectrum, there is a certain class of form fields that arise in type 2b string theory, or let me just call it certain class of fields form fields that show up in these theories, which are called RR form fields. The origins of the name are not very important. They are called Ramon fields, and it has to do with some boundary condition choices. Okay, there are certain class of fields that show up in superstring theory. Superstring theory means the theories which are fully, we believe they are fully consistent. Okay, so there are theories which are not supersymmetric that you can define in string theory, which don't have RR fields, but they not have RR fields, but they are generally, it is not completely clear whether they are fully consistent. Okay, there are classes of string theories which are consistent, which are called superstring theories, which have these fields. Some classes of special classes of these form fields are called RR form fields. Okay, so what happened at some point, and this is one fact. Okay, if there is any point at which you seem lost, just ask me. We can spend one day, or at least most of one day, talking about just the story, because I think it is good to hear the story even if you don't really know about the details too much, because the story can place you in various places when you are reading some paper or something.
Where do these strings live? Where do these strings live?
So the strings are in some sense the fundamental object. Okay, so the way in which you think about it is that the string is basically, at least the way string theory is currently formulated, string theory is a 1 + 1 dimensional field theory. So because so if you look at, if you look at the world sheet of an open string, it's basically 1 + 1 dimensional, right? So you think of it as a 1 + 1 dimensional field theory, and space-time is to be thought of as fields that live on this. You define a field theory here, and the fields that live on here are basically what get interpreted as space-time coordinates, if you like. Okay, so that's the way in which string theory gets space-time. So in some sense, strings are more fundamental than space-time in this picture. But they have the space-time does have a sort of a natural interpretation, because when you can, these fields, the same way that locations, like you can define x mu of t as the location of a particle. Right, so you can think of it as the space-time or the particle's direction or particle's world line as living in space-time, or you can think of it as a 1-dimensional, 0 + 1 dimensional field theory, for which the space-time coordinates are fields on it. You see, these are just two different perspectives. So you can think of this is basically at classical level, at least you can quantize it eventually, but at the classical level, this tau is basically a parameter on this world line, which you can think of as the space-time of that world line on which the x mu's are living. That's one perspective. Another perspective is you can think of this curve as being embedded into a space-time x mu, where this tau is one particular choice of parameterization. Okay, there are two different perspectives, but if you take the perspective that the world sheet is more fundamental, then x mu's are just fields living there. Okay, so that's the picture. Okay, so
the classification of the things is type 1 type 2.
Yeah.
It also has something to do with the dimensionality of the D-branes.
So the string theory will tell you. So in closed strings, the way they are formulated, there are no D-branes to start with. Okay, and in fact that's one of the points that we'll get to in a second, because you will find that one of in some sense one of the most important breakthroughs in my opinion in string theory that happened was Polchinski's observation that in closed string theories you can actually find candidates, in these D-branes that seem to be boundaries of open strings can be thought of as states in closed strings as well, closed string theory as well. So this is in some sense at the basis of, let's say, area safety correspondence and all that. So D-branes are somehow D-branes have this dual Janus kind of interpretation as objects that have, this is already kind of clear here. So they have this interpretation both as in open string theory as well as closed string theory. So Polchinski's observation, very roughly speaking, is that there is a sense in which D-branes can be thought of as states that live also in closed string theory, even though closed string theory a priori need not have had D-branes. Right? Here what I said was that if you have a closed open strings can have D-branes, but they have a dual interpretation, at least according to this, that you can think of it as emission and absorption of closed strings. Okay, so in some sense, the reason why D-branes became so powerful is because of this observation, which I will talk about in a second qualitatively, is that there are certain states in closed string theory which you can interpret also as D-branes. Okay, so the way that argument goes is like this. Okay, so the way that argument goes. So now let's talk about that. So before I talk about that, I have to also say that, so string theory has all these fields. These are the low-lying fields, these are the massless fields of the string theory. So string theory, if you quantize the string theory, you will find that there is a tower of heavy particles as well. Heavy fields or whatever. So string theory is like a theory of an infinite number of fields. Okay, so there's a whole tower of fields, which are all of them are excited states, but the massless fields are these guys. So the other guys, roughly speaking, have masses that are controlled by what is called the tension of the string, and the tension of the string is something that one expects to be at least close to Planck scale in some sense. Okay, and because of which those particles, the masses of these excited particles are sufficiently high that they are not relevant for low energy physics. So we expect to get the low energy physics of string theory from just these fields that are sitting here. Okay, so this is the story. So the point is that because was that a question? No. So because we have this low energy field sitting there, and string theory tells you, string theory has the rules of string theory tell you how scattering of strings work. Okay, so it's another fact which you can spend it's most of Polchinski's book is basically talking about that. So in the first various places, a lot of the book. So you can compute scattering amplitudes for strings. Okay, and because we know the scattering amplitudes for strings, you can also figure out the effective scattering amplitudes for these the low-lying parts of the spectrum. Okay, and it turns out that there are certain natural theories, field theories, which reproduce those scattering amplitudes. Okay, and those are called low energy effective field theories for the string or for string theory. Okay, and for each string theory, there are these low energy effective field theories that you can write down, which reproduce the scattering amplitudes for this low-lying part of the spectrum in string theory, but using a standard conventional bulk effective field theory, which basically means something like what you are familiar with in space, standard field theory, so, and because there is metric there, so these effective field theories will contain Einstein gravity as one piece and action terms for these F's and so on. So very roughly, they will schematically take this kind of a form. S. Let me write it for, S. S is schematically D10x, because string theories automatically tell you, the superstring theories automatically force the dimensionality of the space-time to be 10. Okay? So, and then some root G. Doesn't really matter. So, and I'm not going to write all the pieces. I'll just write some F. This kind of actions you will get. Okay, so the point is that these kinds of actions will reproduce the low energy dynamics of the closed string light fields. Okay, so these are called the bulk effective field theory or the low energy effective action for string theory. That's what this is. Okay, so fine. So, and of course the details, I'm not writing all the fields. First of all, I just want to give you an idea that these are basically just some theories, some Einstein gravity like theories with extra fields in them, and these actions are basically what are called supergravity actions. Okay, so this action that I wrote down, if you start with type 2b string theory here, the explicit specific action that I get here will be called type 2b supergravity. There are some slight subtleties here that I'm glossing over, but this, yeah. Yeah.
14 to 10, that it change if I take some other type of string theory.
So all the consistent string theories live in 10 dimensions. All the consistent, like, so you can, so the point is, essentially what we mean by, so I told you that, these theories that live here are field theories, some two-dimensional field theories, right? So if the two-dimensional field theories, if I take them, roughly speaking, to be massless, free theories, then you will have, these are always going to live in 10 dimensions. So, but you have choice of, this theory is the classes of consistent world sheet theories that you can put here are essentially, is very vast. So that's related to the fact that, it's in some sense, there are, it's essentially already at that level. I think string theory is telling you that there are many consistent universes, okay, which are solutions of all the, this thing. But anyway, so let me not, add more than what I have to say in order to confuse you. So there is the classes of field theories that live here. One of the consistency conditions is this has to be a conformal field theory in 2 dimensions. Okay, so this conformal field theories, but there are many kinds. So if you take the conformal field theory, 2-dimensional conformal field theory, to be a free theory. So if you take it to be a free theory, then essentially what you will get are all 10-dimensional theories. So yeah, so those are the theories that we.
The scattering approach calculated from the closed string quantization, and that from the boundary.
Which boundary?
And this is from the bulk, right?
No. So the bulk. So here, what I mean is, so the notion of bulk here is different from the notion of bulk and boundary in ADS and ADS-CFT. So here, what I mean by bulk is that the string is propagating in a space-time. This x mu is what I'm calling. If you have a string, this is for a particle, so it's something like this. Okay, so there are 2 parameters which control the world sheet, and if the sigma is periodic, it becomes a closed string. It will be like this, something like this, or one of these things. Okay, and this x mu is basically what I'm calling the bulk, because it's propagating in space-time. So, and there are, string theory has its rules for computing scattering amplitudes for strings. Okay, and the scattering amplitudes for strings, if you compute it for, let's say for type 2b string theory or whatever, the low energy or the low lying part of the spectrum, that from that amplitude you can infer what the amplitudes for these scattering of gravitons are, for form fields are, etc. And as I said, the fields that matter to us are these low lying fields. Okay, so so the point is that scattering amplitudes then can again be reproduced from a pure bulk field theory, and this is what that is. So this is essentially, that is what is called a supergravity. Okay, supergravity is basically, or 10-dimensional supergravity is a low energy limit of string theory. So, and this particular, I'm interested in a particular kind of supergravity, which I'm just for the moment calling type 2b supergravity. Okay, so yeah.
When you say supergravity, so we are formulating gravity of superspace.
No. So the point is that I have not told you all the fields that are here. They're here. So this also contains, also here there is extra fields which correspond to spinors. So this conformal field theory that is living here is not necessarily just a bosonic conformal field theory. It also has super or fermionic pieces in it, and there is some worlds, there is some supersymmetry. The theory has some symmetry, which is supersymmetry, which relates these bosons and fermions. So that's where so because of that, here you will also in the space-time. So this is not that these are space-time fields. Okay, so the interpretation of the spectrum of the string is in terms of space-time fields. So those space-time fields, I haven't written the fermions, but there are fermions. So, and because of those fermions, there are these terms, there are extra terms here which are also fermionic. And so this theory actually is also supersymmetric. Okay, and that supersymmetry is why it's called supergravity, because it contains gravity and it's supersymmetric, so it's supergravity. So here note that there are the 2 distinct notions of supersymmetry. One is on the world sheet and one is in space-time, here or here. Okay, so here also you can, at the level of the string itself, you can, at the level of the full spectrum, you can show that the theory is supersymmetric. Not just at the level of supergravity. Okay, so this is a space-time supersymmetry and this is world sheet supersymmetry. Okay, so the point is that world sheet supersymmetry is necessary so that you get consistent, fully consistent descriptions of these scattering amplitudes and all that. And in fact, yeah, its consistency is what forces most of these things. For instance, the dimensionality being 10, yeah, etc., etc. Any other question?
So, by this open closed duality, do we have any relation between the AU and the form fields that we have in the closed?
So, yeah, so in some sense you could say, like, yeah, so ADS-CFT is a statement of that kind, actually. In the end, ADS-CFT is like the simplest, you know, it's in some sense is a statement about such a relationship. ADS-CFT, but at this level it's not obvious how to interpret, how to realize it. We know that intuitively, okay, this looks like this, right? But it's not clear how to actually, you know, if you could, yeah, I mean, it's a, you know, string theory is a complicated theory, so it's not very clear how to act. It's also another thing is that we only know how to compute scattering amplitudes perturbatively in string theory. We know how to compute them by using Feynman diagrams. There is no analog of a path integral definition of string theory where you can just compute the string amplitude just top down. There's no such thing. So that's in some sense the biggest open problem in string theory, if such a construction exists or if it doesn't make sense, etc., etc. Okay, so string theory is only defined in perturbation theory. Or that's what is called perturbative string theory. So in a sense, you could think of ADS-CFT as a particular case in which a non-perturbative definition of string theory is found, sort of by accident. You know, so but it's for a specific, I mean, you know, I think, yeah, let me not get into it. So yeah, so this is the story here. So the point is that, so now the point is that because this is a low energy effective action, you can try to find solutions of this. So it's a 10-dimensional theory, and there exist solutions. So there are essentially, like, basically most of the solutions that we find which are interesting are solutions which are black holes of some kind or empty space, right? So, and it turns out that these guys have solutions which are essentially black hole solutions which are called D-branes, which are solutions of these, you know, these supergravities which have planar horizons, hyperplanar horizons, if you like. Okay, so such solutions can be found. They look, you know, you can look with some metric, with some, of course, some flux will also be there. Okay, because it's a full theory. So, and the point is, so the key observation that Polchinski made is that he argued that these boundaries in open string theory carry the same charges. So if you have gauge fields, you know, RR form fields are some form of gauge fields. So gauge fields basically means that there is some charge coupled to it. There is some charges might be there, okay? So if you, in principle, you don't have to add any charges, but in general, you know, like you could write Maxwell's equations without charges. But the existence of a Maxwell gauge field is a suggestion that maybe there is something that couples to it. Okay, so what Polchinski showed is that these boundaries of open strings, which are basically what we call D-branes, which should not be confused at this stage with P-branes. These are two distinct things at this point. Okay, P-branes are solutions of the low energy effective action coming from closed strings which have planar or hyperplanar horizons, which are essentially black holes of some type. Okay, black holes, they're not spherical horizons, but they are black holes of some type. Okay, so these things, on the other hand, are boundary conditions which for open strings. So the thing that he observed is that if you compute the spectrum of these particles or whatever, you know, or the fields in this theory, one can argue, and this is the part which I will really gloss over, I will not say anything much about it. I mean, you can look at his paper, is that the spectrum of, you know, these boundary conditions can be viewed as things that couple to these gauge fields, or the, you know, these things that couple to these RR form fields. Okay, so these can be viewed as sources of RR form fields, even though these theories are originally living in open strings. Okay, so this is one bit of observation. That is Polchinski's observation, and then the second fact is that these guys, these solutions, also because they contain naturally, because they're descending from these you know, bulk effective action, these things contain, they also are charged under, they're like electrically charged, you know, basically like your Reissner-Nordstrom type black holes. Because if you had F mu nu, we wrote it down earlier, so they have these are black branes. These black branes also contain, they are charged under these form fields. Okay, So the point is that he showed two things. One is that these D-branes in open string theory can be interpreted as sources for RR charges, and he also showed that they preserve the same amount of supersymmetry. Supersymmetry is a symmetry that this theory has. So whenever there is a boundary condition, roughly speaking, it will break half of the supersymmetries. Okay, so it's like translations, if you like. It's supersymmetry is kind of like roughly like a square root of translations. So it's a symmetry, but whatever it is, it's not very important what the symmetry is. But the point is that you can show that these objects satisfy the same symmetries and charges of the p-branes that you see in type 2b. Let's concretize it and make it type 2b string theory. Okay, so this is a statement that he had for all consistent closed string theories, but we will be interested momentarily in the type 2b case, so I'll just talk in the language of type 2b. Okay, yeah. Sorry?
A is the gate field, and it leaves on the D-brane, right?
I mean, yeah, so you can think of mu, so the effective field theory corresponding to open string excitations of D-branes contain this gauge field mu, if you like. So so here I'm basically just saying that here, that's not quite what I'm saying. I'm saying that if you quantize the string with D-brane boundary conditions, open string, I will find in the spectrum of the theory fields that can be interpreted as gauge fields in the bulk spacetime. That's what I'm saying.
Index Newton from is it the space-time index, right?
This mu is, yeah, it's a space. Everything is space-time here. Okay, yeah, everything is space-time here, and yeah. So, but what you said is so true, which is that the low energy dynamics of these. You can think of an effective field theory for A mu's as corresponding to the low energy dynamics of D-branes. Okay, A mu's and whatever else is there in the open string spectrum. Okay, so. So what? So yeah. So this. So this is. So I think I have told most of the essential facts that we needed. So the final bit is that for reasons which again are somewhat technical, people believe that this state that we found here and the state that we found here are the same. Okay? So these are just different regimes of the same object. So in the parameters, for instance, this corresponds to, this low energy theory basically corresponds to a regime where the gravity, G Newton is very large. Oh, sorry, G Newton is very, the back reaction of the branes have been taken into account. So that's the way we think about it. So this is basically the regime where the branes are, so this is the regime where gravity is very weak, and this is the regime where the gravitational back reaction is sufficiently high. Okay, so in another way of saying the same thing is that people sometimes talk about a number of D-branes. So there is a, D-branes can be thought of as a stack of D-branes where one string is starting from somewhere and ending on another one. So if you have n D-branes, an open string can end on one and start on another, etc. So that n, when it becomes large, the idea is that it back reacts on the space-time that is living in, and then you end up getting a supergravity solution, which is this B-brane. So this is the picture. Okay, so yeah, it's not, so it's not, what I've told you is not as sketchy as one might think. I've told you actually quite a bit of the story. There are pieces where I'm really not emphasizing. One of them is why people believe it is called, kind of related to the, statements about BPS protection and various things like that. It doesn't matter. None of these things are very important. But the point being that this D-brane and this guy we think they are the same thing. Okay, so is that story clear? So if that story is clear, we can talk about Maldecena's derivation or argument. So just the general story is enough. Yeah.
Over there, when you say state, I understand like the solution of that action.
Correct. Yeah.
When you say state over this D-brane, what do you mean with the open?
I didn't. Yeah. So the point is that, like in this, yeah, that's a good question. So the point is that, like these objects. The non-trivial fact about these D-branes is that they carry Ramon charges, right? So these RR charges. So the RR charges naturally occur in closed string theory. So you give it the interpretation that these D-branes, which acted as sources for open strings, are also states in the closed string theory. So the statement is that, so these RR form fields are basically are a part of closed string theory. right? And here we started out our story basically by saying that D-branes have some boundary conditions for open strings or whatever. But Polchinski's argument, which I have not told you, is basically that these these guys carry. So because using this picture essentially, okay, so this picture, because of this loop interpretation, you can argue that these guys, the closed string states that are emitted from this D-brane, you can argue that they carry the RR charges of the closed string. So that's the argument he made. So once you have the statement that these RR charges, so these D-branes are basically sources for RR form fields, then you can think of them. So the idea is that you should think of them as states that live in the full type 2B string theory. Okay, even though they are not accessible in this perturbative quantization that we did.
So D-brane itself is state.
Yes, in the full string theory, we expect that these D-branes are states of the closed string. So that's the idea. And so these states are basically, this is just basically an ordinary amplitude for a state to emit something, a closed string, and capture it here. So this, you can think of it as this, with something in between. Okay, so this is a D-brane state, if you like. Okay, so, and this is, versions of this calculation is what you can use to show that D-branes carry these Ramon charges. So, is that fine? So, yeah. So, yeah, I think this is, this is essentially Polchinski's calculation in one way or another. Okay, and so the thing that I have not really, so this is kind of an outline enough for if you want to go look at it, is kind of good enough. So the one thing that I have not told you is that because of the supersymmetry conditions, these states are in some sense protected. So we expect that these states should still remain as states even after the theory starts back reacting, the parameters and the gravity becomes more, you tune the couplings. Even after you make the couplings, become large or whatever, even if you change the parameters of the theory, the state still will stay. It's not going to break up into some other states which you cannot trace. So even as you tune the parameters of the theory, which are basically the n, if you like, of the number of D-branes, as well as let's say G string or something. G string is, that I did not say anything about, but G string is the coupling constant of the string. Okay, so string theory has a coupling constant. As I said, there is a perturbation theory. So as you tune these things, the expectation is that it will land you in the, those states can be sort of faithfully tracked to the states that live here. Okay, so if you have n D-branes living here, and if n is sufficiently large, that object can be interpreted as the P-brane of string theory with some amount of flux. Okay.
So supersymmetry is necessary for that.
This argument is, yeah, absolutely, yes. Supersymmetry is, if supersymmetry is not there, you cannot make this kind of protection argument. So, yeah. Okay. So, now the point is that, so the next point, so now we can, I think if this is clear, then we can talk about what Maldecena's argument was for ADS-CFT. So what Maldecena did was, so let me just write so he starts with, so n D3 branes in the limit when n is large. Okay, so this is the setup where you expect this thing to apply. Okay, so there's a large number of D-branes, so you expect back reaction, the solution to have back reacted. Okay, n is, you can, in fact, you can compute, for instance, the weight of the D-brane and so on. So if you compute it with large n, you expect it to be massive, and then you expect it to back react, and then you expect the supergravity picture to be the valid one, and not the perturbative string theory one. Okay? So in this limit, you can write down some solution. This solution is known. I'm not going to write it, but you can just look it up. Okay? And you can check that it is a solution of this type 2B supergravity equations of motion. So it's straightforward. And it preserves half the supersymmetries, because it's basically a brane. So whenever you have one brane sitting like this, it breaks half of the supersymmetries of the background. So, okay? So in 10 dimension, there are 32 supersymmetries. So this brane solution will break half of them, so it has 16 supersymmetries. Okay, so not very important, but just an example. So what he wanted to look at, so this is basically, so this is the, black 3-brane solution of supergravity. Solution of 2b supergravity. Yeah.
So what is the n of that we consider the supergravity?
So n is not the most useful quantifier. So n, you can, so this type 2 is basically saying that it is n equal to 2 in 10 dimensions. Okay, so 2 is like the what is more meaningful is basically a count of the supercharges. So because it's like this n, so there is a notion of a minimal spinner in any dimension. So the number of supercharges divided by the number of components of the minimal spinner is what is called n. For instance, here is 2. So that's just it's not a very, it's just historically it's there. It's better to count the number of supercharges. Okay, so also that n is not related to this n. This n is the number of branes. Okay, which it will turn out will correspond to, I'll get to that in a second. So this black 3-brane solution of type 2b Sugra, so this is what he started. Okay, and so he looked at the low energy limit. Okay, so and this is the sort of he looked at the low energy limit of the solution. So, but he implemented the low energy limit in an interesting way. And that interesting way is basically that whenever you have a black hole, so this is essentially a black hole, a black brane, but a black hole. So the way in which you consider its low energy limit is by he looked at the solution close to its horizon. Okay, because near the horizon there is redshift. So geometrically, the way in which you implement the low energy limit for this solution, he took a near horizon limit. Near horizon limit. Okay, so which basically corresponds to, roughly speaking, to sending some r to 0 in the D3 brane solution. Okay, so and if you do that, what you find is that this black 3-brane metric basically becomes the metric of an ADS5 times S5 geometry, and there is this 5, there is a D3 brane solutions have a 5 form. Okay, so here I did not specify what forms were there, but D3 brane solutions have a 5 form sitting there. So there is a, is basically an F5 flux will also be there, which also you can write down. Okay? Is that fine? So you start with some solution. Think of this as some fancy Schwarzschild-like solution. It's not even very fancy, you can look it up. So this solution, you take some near horizon limit, you will get a new metric, but now the black hole or the brane has completely gone. And you are left with the near horizon geometry of that brane, which has the structure of a ADS5 times S5 geometry. Okay, so you can, this metric in fact you can write very explicitly. So let me just write it for you. I'm suppressing some scales. So this is the metric. Okay, so this is basically what is called ADS5. So this is a 3 spatial dimensions. This is a time dimension. There is an extra r. So together there is 5 dimensions here, and then there is a sphere sitting here, and the radius of the sphere is a constant. Okay, so this is the geometry that you get. Okay, so and the point is the 5 form flux, we don't care. It's some constant it will be. It will be a constant flux. Okay, so through this S5. So this S5, if it, like the equations of motion for these kinds of space, these kinds of Lagrangians, it turns out that you need a flux to stabilize that sphere. Otherwise, it will just collapse. Okay, so this is the geometry. So, so this is the geometry that you get. So, okay, so this is this observation. The first observation is basically that you start with type 2b supergravity, take the low energy limit, and then you end up with some, some near horizon geometry which looks like ADS5 times S5. Fine? So, so that's the first observation. So then what he does is, the second observation is basically that you can, so this theory, so the low energy limit, because these D-branes, as I said, have this, this Janus property, right, which is that they can be both thought of in closed string language, which is what that is, and they can also be thought of in in the open string language. And it turns out that this is something that, just from knowing the scattering amplitudes here. So if you know the scattering, like I told you, that open string scattering amplitudes can be computed, from which you can infer the low energy effective action of open strings. Okay, so here I was talking about the low energy effective action of closed strings, but you can also do it for open strings around a D3 brane. And it turns out that that action is, is a very standard QCD-like action, which is called the n equal to 4. So now this is just D3 branes in the open string picture. In open string picture. Now note that, so that argument only applies when n is large. Okay? D3 branes in open string picture. So the low energy open string EFT is what is called here, this n is different, n equal to 4 SUN, where this n is the number of branes, super Yang-Mills theory. So it's again a fancy name, but it's basically just a QCD-like theory, except it has, instead of quarks in the fundamental representation, you have scalars in the adjoint representation. Okay, that's really the biggest difference, I would say. Okay, so and then there are some spinors also because the theory is supersymmetric. Okay, so he looks at D3 branes and says that at the large n limit, in the large n limit, we should be, the supergravity or the type 2b supergravity description should be reliable. He looks at the brane solution, the p-brane solution, and he implements the low energy limit by taking a near horizon limit on the solution. Okay, and if you do that, you find that this is the metric that you get. And the second thing that he does is that the same thing, but now you look at the open string picture, and low energy effective action, this is people have, this has been done long before. And you can just look at, this is the action that you get. This is some explicit action. It's like a QCD action. So then the claim is that because this theory, so this theory, note that we don't have access to the full string theory at, this is kind of inferred, right? We had a perturbative string theory, then we said that the bulk effective action is basically some 2b supergravity. But once you get to this p-brane solution, we don't know how to do string theory there. We are using this bulk effective field theory, this bulk 2b supergravity, in order to write down a solution, and we are using the fact that it is supersymmetric in order to make a conclusion about it. Okay, that it should exist in the string theory. This is the claim. Because it's not directly, this solution, this 2b supergravity solution is a supergravity solution. It's basically like a solution of Einstein gravity with some fields. Okay? And that solution, but we trust that that solution should be meaningful because it is a supersymmetry protected solution, and so we expect that it should actually be a solution of string theory itself. Okay, so that's the thing. And so, but the point is that this argument only works when n is large. So here the large n is very important. Okay? So, but this description is valid at all times. Okay? And because, so it's natural to claim that this, in the large, both of these things are supposed to be the same object. So that's essentially the statement of ADS-CFT duality. So the claim would be that this n equal to 4 SUN super Yang-Mills theory is basically the same thing as this guy. Or if you could make a definition of string theory at finite n, and not just in the supergravity limit, that should be dual or equivalent to this theory. Okay, so at very large n, this has a dual description in terms of that. Okay, very large n, and there is also another parameter which is important, but let me not get into that right now. So the general statement at least should be sort of clear, which is that this statement, the gravity description, is accessible to at a large n when the branes are back reacting and then there is a black hole like solution, and you take the near horizon limit and there is a gravitational description. And here, so this is basically valid at all n. So we expect that the string theory description of that, which is valid in the closed string description of that at finite n, should be actually be dual to this construction. So this can be used to understand that theory at finite n. That's what makes us interesting. Okay, I don't know if the statement was clear, so let me write that down. So type 2b string theory on asymptotically ADS5 times S5 space times. It's from flux. Let me suppress the flux. with some space-time is equal to n equal to 4 SYM with SUN gauge group. Okay, so this is the statement of the ADS-CFT, the original ADS-CFT correspondence. Okay, so I'll write down some parameters because how these theories are matched to each other. So first thing is, so any questions? The overall picture is all we are looking for here. You don't have to worry too much if some detail you're not, but you can ask the detail anyway and I'll tell you whether it's important or not if you want. Yeah?
Why are we writing asymptotic?
That's a good question. So the point is that, so here what we have done is we have taken the near horizon limit and we have found that this is essentially the vacuum of the theory. So I think maybe you can ask that question once I talk about the ADS, the implementation of the ADS-CFT correspondence. That might be a slightly better place to look at, because how do you define a quantum gravity theory? The way you define a quantum gravity theory is by specifying how at far away from everything else, how the space-time behaves. That's how you define a quantum gravity theory. So this is in some sense the ground state of that quantum gravity theory. So ADS 5 times S5 is the ground state, and excitations on that state are basically the full spectrum of string theory or gravity or black holes or whatever that live in that space. But far away from everything, it should look like ADS 5 times S5. Okay, so that's the reason why, because this is not, note that this is not a statement about, it's not a correspondence, it's not a correspondence between one state with another state. This is a statement about all the fluctuations that happen in the low energy limit of this guy is dual to this particular theory. That's a statement. It's not a statement connecting one state to another state. It's a statement about a theory with another theory. Okay, and this is a theory, and so that is also a theory. So here I am just writing down essentially just the ground state of that theory. Okay, any other question? Okay, so let me say a few words about the various parameters in the theory. So the first one, so in string theory you have a parameter called G string, okay, and there is something which is also called, there is some parameter which is called the length of the string or the tension of the string, depending on 1 over alpha or 1 over L, So alpha prime is basically captures the tension of the string, and it's a dimension full quantity. This is a dimensionless quantity. Okay? So there are two parameters that essentially define string theory. One dimensionless, which is called the string coupling, and alpha prime, which is called, string tension or inverse string tension. Okay? So, etc., etc. Okay, so there are two parameters on the string theory side. Okay, and so this alpha prime is sometimes also written as L string square to confuse you even more. So it's an unnecessary definition. So, and the ADS-CFT correspondence basically says that there is, on this side, so the n equal for, these are the parameters on the string theory side. Okay, and the parameters on this side, for as any theory or any gauge theory, there will be a Yang-Mills coupling. Okay, so this is basically the analog of if you have your Maxwell's action, there will be some f squared d4x, right? So this guy here is, if you make this Yang-Mills, that's basically the coupling. So the point is that this theory is so highly symmetric that it has only two parameters. One is this gauge group rank n, and the second is this coupling. That's it. So in that sense, it is much simpler than QCD. QCD, for instance, you have the quark masses, this, that, everything, and QCD also has this feature that its coupling runs with energy scale. So none of this is true. This is a conformal field theory, and it's exactly conformal, which means that if you specify the coupling G square Yang-Mills, it's a parameter. Okay? So this G square Yang-Mills and N are the two parameters on the gauge theory side. On the string theory side, we have GS and alpha prime, or equivalently LS square. Okay? So, the correspondence. So, and also note that at least in the supergravity limit, this L is a parameter of the theory. Okay, the L is basically setting in the scale of the ADS 5 times S5, the size of the sphere, if you like. Okay, so those are basically the three parameters that you have here. And that is important because here we need, this GS, alpha prime, GS is dimensionless, and both of these guys are dimensionless. because this is a conformal field theory. N is just some number, like 10,000, 10 to the power whatever. So and G square Yang Mills is some dimension less number because it's a conformal field theory. But here we had GS and a dimension full number. So which means that we need to have another dimension full guy in order to get a dimension less parameter so that the comparison is fine. Okay? And the comparison, this is, let's call them Maldecena formulas, even though some of them were kind of known even before. This one was known before. So Maldecena, this is the formula. Let me write it. L to the 4 by GS. Okay, so these are the two formulas that he wrote down. Am I right? Yeah, that's right. Alpha prime square has dimensions of length. So L4 by GS alpha prime square is N. So these are the two formulas that relate the bulk and the boundary. So, so a couple of interesting or whatever facts, or maybe I'll talk about them later. So, okay, so I'll just write down. So this completely defines a map between the bulk and the boundary, at least in the sort of the supergravity limit where L is etc. are well defined. Okay, so yeah. So and one more one more formula which is oftentimes useful is you can GS square times LS to the 8 is the G Newton in 10 dimensions. Okay, there might be I mean, let me write it like this. There might be a factor of, sometimes I think it depends on 8 pi or something. I don't remember. Probably not. I think it is probably exact. But so this is sometimes useful. So this is the G Newton in 10 dimensions, which you get from by doing string theory calculations. You can show. Okay, by computing. Essentially, all of these things are fixed. How you do the calculation in string theory, and at low energies, it should reduce to standard gravity type of calculations. So if you know the string theory amplitude and how the couplings work in string theory, you can map it to the string theory, the gravity results that you're familiar with. Okay? So the graviton scattering should, for instance, be controlled by this. So in string theory, it will show this coefficient, so we know that this has to match with this. That's the way you fix it. Okay? So, so this is just a useful formula, but these are the sort of the defining Maldecena formulas for radius CFT. And any questions? And one reason why it is sort of interesting to write it this way is because you can, so this is also is L Planck to the power 8. Okay, I think this actually is equal exactly, and this is more like, I think there might be an 8 pi or something. Okay, and these are all formulas that are kind of worth remembering, and the way you remember this is that A by 4G is entropy in any dimension, where A is the codimension 2 area. Right, that's Hawking's formula. So and area is, so it has to be 2 dimensions less than 10. That's how we know this. Okay, so area by L Planck, some area is some dimension, length dimension d minus 2. So the L Planck has to compensate for that. So that's how you fix this L Planck to the power 8. But I forget, I think there's probably an 8 pi sitting here. This thing I'm pretty sure is correct. So these are 100% correct. These two are, maybe there is an order 1 number missing, two or something. Okay, so this is, so any questions? I think it was a more successful introduction to radius CFT than I expected. I thought it would be a disaster. Yeah.
So you stated that the theory now is on the boundary. So how do we identify?
No, so far I have not said that. I've not said that. It's like, so this is, I'm still at the place where Maldecena left it. So here the holography, he did not realize that it was a holographic theory. So that was Witten really like, who came up with this observation that the duality should really be interpreted as a holographic duality. So, and the hint is basically that ADS 5 is 5-dimensional, and inside here, this is basically the 3 plus 1 dimensional Minkowski space. Okay? So when R is going to infinity, note that this compact space is just sitting there at the same radius. So when R is going to infinity, this guy is very large. Okay, so this space-time is getting very large, and if you're looking at some fixed large radius, this guy drops off, R equal to constant, this drops off, and this is much smaller than this. Okay, so this is the place where all the action is happening. Okay, so near the boundary, the sphere is irrelevant. So that's the way in which we'll get to that. So that's the holographic aspect is what we really care about. Okay, so this is, right now this is a string theory duality. So there was an era in dualities. I started doing physics pretty much at the end of that era, which is in the later part of 90s. So this ADS-CFT was kind of the culmination duality. So there were a lot of dualities people discovered, and everything, all the string theories, everything seemed to be equal to each other. So there was a time when this was the case, and in some sense, I think that, so there was a generation, so the generation that sort of came after me, ADS-CFT became their central thing. So I think there is a generational gap between people who are slightly, old, like me. So the way to tell the difference is those who have studied heterotic string, which is a particular kind of string theory, which is was kind of one of the main things that people used to study at the time, and those who have kind of, skipped over heterotic string and have started with ADS-CFT. So this is really what all you need to do research in higher energy physics at this stage is ADS-CFT. You don't have to know. I mean, people might disagree, but reality is reality, So heterotic string is kind of, it's important. I'm not saying that it's not important. I think it's a very important thing, but may not be the most important thing that one needs to study at this time in history. So I might eat my words, who knows? So, but yeah, so anyway, so this is the story. So any more questions? Any questions?
So we get the solution, it is 5 times 5, the near horizon.
Yes.
Near the horizon, the metric looks like it is 10 as 5, it is the whole space time, like it looks like it is 10.
It is, so you take the metric and you take the near horizon limit. So it's the near horizon part of the geometry. So in that sense, this geometry, if you look at R going to infinity, you no longer find asymptotically flat spacetime. So here, for instance, the D3-brane solution, the black 3-brane solution, if you look far away from it, the spacetime basically looks flat. Except, of course, there is a transverse horizon sitting like that is spread out all across this thing. But in the transverse directions, if you go far enough, spacetime becomes flat. So that's not the case here. Here ADS-5 is basically, it has warping, there is a curvature. And another thing is that these black 3-brane solutions, which are supersymmetric, they are extremal black holes in some sense. So extremal black holes, so only for extremal black holes you can sort of unambiguously take these near horizon limits. So when I was doing, for instance, for starting with Schwarzschild or something and taking the near horizon limit, you would typically find a Rindler geometry. That's not what happens for extremal black holes. So extremal black holes, if you take a near horizon geometry, you will always find an ADS piece. Okay, even for standard, let's take Reissner-Nordstrom black hole, charged black hole in 4 dimensions. You take the Reissner-Nordstrom black hole, make it extremal, and take the near horizon limit. I have not shown you how to do it, but it's a trivial calculation. This calculation is trivial. If you look at Maldecena's paper, there are hardly any calculations. It's just the idea is very interesting and powerful. Okay, so the point is, so if you look at the near horizon limit, you will find in those cases the near horizon limit is completely well defined. So you can just take it very unambiguously and you will get this. It's part of the reason why extremal black holes are somehow easier to understand than finite temperature black holes. One of the reasons. Okay, so
people also say that D-branes also produce some throat kind of.
yeah, so that's essentially the fact that we are going close to the throat is why the ADS part is coming out. The ADS is, if you look at this geometry, it has some kind of a, there is a warp factor. What they mean by ADS throat is that, it's really the same as statement as, if you have, let's say, an extremal black hole, it will have this kind of a structure. So it will be a double zero horizon. Plus let's say I'm working in, this is basically the extremal, Reissner-Nordstrom black hole. So this warp factor, if you zoom in close to it, you can think of it as a throat in some sense. That's all what they mean by that. It's not, you can draw some pictures and convince yourself that the warp factor is changing in a particular way. And here, you can already see sort of the similarity here. Note that this is, so this here is almost like this guy here, right? So that's where the near horizon limit is coming from. So in the D3-brane case, this is what Maldecena did. So this was sort of the main observation, let's say technical observation in Maldecena's paper. And the second fact is the observation that these two things are the same. And these all came sort of from, like a decade almost of work on black holes in string theory. So this is kind of like, so there is, it was kind of in the air. This is what I've heard from people who were like active in the time that ADS-CFT was sort of in the air. I don't know what air means. I've heard that, I'm quoting somebody, I'm not naming the person, but I've heard that because of because of the fact that black holes are, we made a lot of progress on black holes in string theory at that time. Okay, and then like starting from Strominger-Waffa entropy counting calculation and so on, and from there, and this is ADS-CFT sort of kind of explains why that calculations all work. And it's somehow much more powerful because it's not just a count of the ground state degeneracy, which is what entropy is in those cases. Here it is saying that there is a full theory which is dual to another theory. Somehow he started with a supersymmetric system and we took a near horizon limit and we found a theory, and the theory of course can have non-supersymmetric states in it. It's somehow magical. This is quite magical. It's really surprising in some sense. First of all, that you kind of managed to guess a quantum gravity theory. Like this is quantum gravity. Like we were trying to do quantum gravity, then the perspective has changed, and somebody has given you a quantum gravity theory. But then it really is quantum gravity. It's much more quantum than you thought. Which is that people were trying to quantize general relativity and do various things, path integrals, perturbative quantization, loop quantum gravity, whatever. Some of those things are interesting things and we use them. But the point was that this is somehow immediately showing that it is manifestly holographic, as you will see, because it's, first of all, its dimension is less. You can already see that this is a 4-dimensional theory. Okay, that's ADS-5. So that's one. And the second fact is basically that it also ties with expectations from entropy and so on and so forth. And observables are all at the boundary. This is another feature of gravity. I think I mentioned that last time, right? So this is. So those are that's the kind of I think the story time is over. So I guess, but I think it is okay. I think the lecture went better than I expected. So I was kind of worried that we will not get anything useful. It will just look like a complete story. But I think it is. Better than that. So what we'll do is, let me any questions? Any questions? Maybe I don't know whether I have time to start something else. Maybe I'll just start. I think I'll just talk about ADS. I think it's 12. What is the time now?
12:07.
Yeah. So I think I'll use like 10 to 15 minutes, and I think is enough for me to talk about ADS geometry. Okay, so now the point is, okay, so so now let's study ADS spaces. Okay, so ADS spaces, and asymptotically ADS spaces are somehow dual to conformal field theories. And conformal field theories are basically quantum gravities in ADS space. That's sort of the punchline. So let's look at ADS space. I'll look at in general dimensions. Okay, so generally speaking, we will write it as ADS D+1. So it's a D+1 dimensional ADS space. So the metric. So I wrote the metric down for ADS times S. In what is that coordinate that I wrote is called the Poincare patch of ADS. I'll say that in a second. But now I'm going to write it in a slightly different coordinate. And this R is not the same thing as the R that I wrote down. Okay. So this is the metric. This is sometimes called the global ADS metric. Global form of ADS, one of the global forms of ADS. And this L is basically called the ADS length scale. L is ADS length scale. An important point about the solution is that this is not a solution of R mu nu or G mu nu equal to 0. You can get this only as a solution if there is a negative cosmological constant. Okay, and this, I forget the precise formula. So it's 1 by L is basically like cosmological constant, maybe some power here. Okay, so it's roughly like that. Okay, so if you solve Einstein's equation with a cosmological constant, negative cosmological constant, this is essentially the ground state of the theory. Ground state means the lowest energy solution. Okay, so and we will often set L equal to 1 because it's a dimension-full quantity. Okay, so and as Rairth was asking, so the question is, so what we mean by quantum gravity in ADS is an interesting question, right? I mean, it's not like if ADS is just some state. ADS, the way I described it, ADS is some state. So what do you mean by quantum gravity in ADS? What you mean is the same sense that one might think about quantum gravity in flat space, which is that you think of, and in some sense, this is a question that itself became sort of clear through the advent of ADS-CFT, I would say. Because the idea that boundary conditions are very important for defining quantum gravity became only clear only via this, the fact that this is a holographic theory and so on. So the point is that asymptotically ADS is basically any space-time. I'm not going to make it too precise. You can make it very technically precise with various assumptions and so on. But what it basically means is that at large R, the space-time looks like this. In the same sense that asymptotically flat means at large R, it looks like Minkowski space. Okay, it's the same sense that asymptotically ADS means. And what we mean by quantum gravity in ADS is the Hilbert space of the theory we imagine is built of states which asymptotically will look like empty ADS spacetime. That's what we mean by the quantum gravity in ADS. Okay, and as you will see, the definition of quantum gravity in ADS in some ways is much more clearer and cleaner than in flat space, because flat space often has this feeling of an open system, because things can leave. Okay, as you will see in this geometry, if you throw something to the boundary, because of this the curvature L here, it will always come back to you. Okay, so it's kind of like a box for gravity. So that's the reason why this is a very interesting, this is one of the few places where you can probably it's like quantum gravity in a box. Literally that's what it is. Okay, so you can compute the geodesics for somebody sitting in the center of ADS and throwing something, and you will find that it comes back to you. So this is the reason why it is somehow simple. Unlike flat space, where there is, if you write down the Penrose diagram for flat space, I mean writing in this two-sided form, the proper time to the boundary, spatial boundary, is infinite. If the radiation from a black hole leaves the black hole, it just goes on forever. There is an infinite amount of volume at infinity. Okay, and in an infinite amount of proper time at infinity. So in ADS, there will be an infinite amount of volume at infinity, but there isn't an infinite amount of proper time at infinity. So if you send something there, it will come back to you in finite time. So to make that clear, so let me write this R, I'm going to write it as tan rho. I'm making a new definition. So, and if you do that, this is another form of this is global form 1, and I'm going to write the global form 2. Global form basically means that these coordinate systems cover all of ADS space. That's all it means. Okay, so if you have a chart or a coordinate system, need not cover all of the space-time, right? But these two coordinates, they will cover all of the space-time. So this is minus dt square plus d rho square plus sine square rho d omega d minus 2 square. Okay, and because of this coordinate transformation, because r is going from 0 to infinity, this t is going from minus infinity to infinity, and the angles are whatever the angles are of a sphere. Okay, so this is r is going from 0 to infinity, time is going from here. So because of this definition, now it is going from 0 to pi by 2. Okay, and and this is just an overall conformal factor. Let's just remove it because that doesn't affect the causal structure. So, and if you do that, you can write you can write a Penrose-like diagram for the space-time. So you can write a Penrose-like diagram. Okay, I'm basically going to draw it like a cylinder, which is that rho is 0 here. So this is rho going from 0 to pi by 2. The key point is that it's only a finite coordinate range in rho. Okay, and this t is basically this. It's just going from it's going from minus infinity to infinity. This is an infinite cylinder. Okay, and this sphere, I'm just writing one. You can think of, if it is just ADS3, will be just a circle. If it is higher dimension, this is a sphere, but it doesn't matter. Okay, so, and that's our picture. So the key point here is that what I'm claiming is that if you send a light ray, goes at 45 degrees, and it'll come back here, and there is only a finite amount of proper time between sending and receiving. So of course, for a light ray, you have to put some reflecting boundary condition here so that it comes back. You have to specify boundary condition, otherwise it's not clear what happens. So, and we will see that, for various purposes, the reflecting type of boundary condition is natural. Okay, and if it is some other thing which is basically if it's a time-like object that you send, it will actually physically come back. It will come back like this. For a light-like thing, it will actually reach the boundary, so you need to specify a boundary condition. But if it is a time-like thing, it will actually come back because those are the geodesics of the space. Okay. So yeah, so this is the reason why you think of ADS as a box. Okay, and yeah, it's a box for gravity, unlike Minkowski space, and not an open system. And yeah, one very important fact, and this is a super important fact, is that the isometries of ADS. So if you know Minkowski space, we know what are the isometries of ADS? Minkowski? Poincare. Poincare. So Poincare, Lorentz transformations and translations are the isometries of Minkowski space. It means that the form of the metric will not change. So it turns out, this is, sometimes it is written as ISO, 3,1. This is the Poincare group in flat space, flat or Minkowski space, the isometry of Minkowski space. So the claim, and this is again, so as I said, we are basically interested in the facts related to this, and if you can treat all of them as exercise and do them if you like, and if you are really going to work on this field, I strongly encourage you to do that as well. But we are not going to derive all these facts. They're straightforward. So this is the isometry group of ADS D plus 1. Okay? SO D, 2. So this will turn out to be very important when we discuss the dual conformal field theory. And you can sort of see at least part of it in this form that I wrote earlier. So I wrote the ADS. So this is Poincare patch of ADS. So this coordinate system but does not cover all of the space. Okay, it only covers, roughly speaking, a slice like this. So this region is what is called the Poincare patch. Okay, so some coordinate region which covers a piece of ADS but not all of it. So that's what this guy covers. But the advantage of this guy is that, for instance, the SO, the SO D, 1 part of the space symmetry is already manifest here. You can also see that other symmetries are fairly easy to see here. In the Poincare patch, this SO D, 2 is easy to see, fairly easy to see. Okay, because it's here, this is obviously Poincare transformations of this one lower dimension is obviously there, so that's inside here already. And then the extra stuff, which is some scaling, etc., which we will see, are also fairly easy to see. So if you want to check the isometries of ADS D plus 1, I would recommend trying it here rather than in these coordinates. Okay? So that's.
So D plus 1, this one, the patch.
Which one?
The D square equal to D. Because that's only one time equal.
Which one are you talking about? Sorry, this one. Or this one. No, I'm not saying that. See, this is, it's not all of it is visible here. So this is only a subset of this. This basically, if this is ADS D plus 1, this is basically Minkowski D. Right? So Minkowski D means that the SO D minus 1, 1 is what is realized there. Right? So only that of, not all of SO D, 2 is realized there. I'm just saying that it is easier to see all of it. At least this much is already immediately clear. Here note that only the SO D minus 2 is clear, because the sphere has SO D minus 2, and that's the only symmetry that is really visible. And then there is a time translation. So those are the only two things that are manifestly visible. But here, more is visible. That's all I'm saying. So here, for instance, you have a Poincare translation, then there is a translations associated to all of them. So the full Poincare group of Minkowski D is already visible. And that is contained inside this. That's the claim. Okay? So that's what it is. And the conformal transformation, there is some extra symmetries which are also easy to see here. So
this is the whole patch, like whole shaded region inside
the whole shaded region, that's right. This whole region. So, and the boundary, so this is something that you might be familiar with. This boundary, this scarf that is sitting here, is basically this Penrose diagram of flat space. Okay? So this scarf, if you open it up, that's basically just this. And that's this Minkowski space. Okay? So
this is embedded inside the Minkowski.
Sorry?
ADS is embedded inside the...
No, here I'm not talking about embedding ADS. So ADS can be thought of as embedded in some higher dimensional Minkowski-like spaces, but that is not what I'm talking about here. I'm not introducing that at all, because that's for me that's a distraction. So what I'm saying here is that ADS metric in itself contains a Minkowski piece of lower dimension. So this is the reason why when R goes to infinity, this piece is what we will interpret as the boundary of ADS, conformal boundary of ADS. So that's why there's an R square. So it is some factor sitting there, but otherwise this is the boundary of ADS. Okay, so the Minkowski is noted as one lower dimension. It's Minkowski, D. Okay, and that's one lower dimension than this guy. And Minkowski D has, SO D minus 1 comma 1 Lorentz group plus, if you like, translations, RD. So these are the symmetries of this space, and those are contained here. So that's what we'll talk about. So what's the time now? Yeah, so I think they're basically done. So I'll just make some qualitative comments, which is that, so the point is that as I said, we think of ADS space as the ground state of quantum gravity in ADS. Quantum gravity in asymptotically ADS spacetimes. Okay? So this is the ground state, and if there is no symmetry breaking, we expect that the ground states of theories will exhibit all the symmetries of the theory. Okay, so if there is symmetry breaking, of course there is some, you might lose some symmetry, but generally speaking, of ground states of theories will manifest all the symmetries of whatever the theory that you're talking about. So here we expect that this SO D comma 2 being an isometry of this ADS D plus 1, we expect it to be the symmetry of quantum gravity in ADS D plus 1. So the Hamiltonian of quantum gravity in ADS D plus 1, whatever it might be, we expect that it should have an SO D comma 2 symmetry. Okay, and so this is one fact. And the second fact, so it turns out that in hindsight, of course, it feels like you could have guessed it on general grounds that ADS-CFT correspondence should some level work. So many of the recent introductions of ADS-CFT, for instance, never talk about D-branes or anything. So they just basically derive it or sort of motivate it just by general arguments. So I'm just going to give you, sort of one argument, which is that there is an SO D comma 2 symmetry. And the second fact is, because we know holography, we expect that the theory should be living on the conformal boundary of ADS, which, at least in Poincare patch, it's the most obvious candidate is this Minkowski space. Okay, so we want to have a theory that lives in D-dimensional Minkowski space, which has SO D comma 2 symmetry. And there is a well-known class of theories of this kind, and they are called conformal field theories. Okay, so in that sense, so so I think that's an excellent place for me to stop. We'll start with some similar things, continue from here. Any questions? So this is sort of the indirect motivation. So from the way I talked about this theory, this N equal 4 superangles theory, that theory is conformal. That's a very important fact. Okay. In fact, I think many people were talking about large N gauge theories for a very long time, and they expected it to be dual to string theories, as I mentioned long ago. So, but the thing that oftentimes was missed was because of the influence of QCD, we were always looking at confining gauge theories. Large N confining gauge theories where the coupling depends on the scale. Okay, the coupling constant is running with the scale. That's the kind of theories that people are looking at. So in some sense, the big realization of ADS-CFT correspondence, another big realization of ADS-CFT correspondence is that conformal theories in the large N, if you look at large N conformal gauge theories, large N gauge theories which are conformal instead of confining, then there is a natural, there is this dual string theory sort of falls on your hand somehow, the ADS string theory. Okay, so that is so there are many remarkable ideas in that in this observation. So in today's class we covered like many things which are sort of took many years for people to develop. But it's an interesting story. That's it. Yeah.